So I want you to try, I hope that you can recognize that the last few chapters have been interrelated with each other. In other words, we kind of introduced this idea of, of really using normal distributions and to estimate a point estimate for a population based on a sample. And then we extended that idea to saying, we don't really know how accurate that 1 point estimate is for the whole population mean or the population proportion. So what we want to do is we'll give a range, right? We'll say within a certain confidence level, we're pretty sure that the population proportion will be here. And so this next chapter, hypothesis testing, is a further extension of the same ideas, which means this whole exam, when you get down to it, it's going to be these kind of extensions of the same ideas. Okay, so if you're feeling weak on one of them, you're feeling weak on all of them, if that makes sense. And so I guess like my urging here is to say, as you go through the homeworks, don't settle for just being able to get it right. You need to settle for understanding it, which means you may have to go through it more than once. Like, again, not for your grade, but for like, I got to understand this enough that I can then do an exam. So chapter 9 is on what's called hypothesis testing. So this is how we use a lot of these concepts in a real world scenario. This gets used a lot in sciences as well as in business. You've probably noticed by now that business is like, I don't know, half art and half science. There's parts of it that are just like, what does our intuition tell us about what the market wants? But then there's also a scientific side to it where we're going to measure data and make decisions based on that data. So in science, you learn about hypotheses, which is like some educated guess as what's going to happen when you perform an experiment, right? And then you test it and see if it actually happens. So that's what we're going to do here, is we're going to learn about this process from a statistical standpoint. All right. So there's two terms that we really need to know. The first is called the null hypothesis, and then the second is called the alternative hypothesis. So the null hypothesis is that educated guess, or they call it a tentative assumption about a population parameter. We think the population mean will be probably this, or we think the population mean will be greater than this or less than this. Okay, that would be our null hypothesis. It's the tentative assumption, or the thing that we think. And then the alternative hypothesis is, sometimes it's called the research hypothesis. It's like it's what we're gonna do to test it. So if I say, I think the population mean is 20, then the alternative hypothesis would be the population mean is not 20, right? Or if I'd say my null hypothesis is, I think the population mean is less than 20, or less than or equal to 20, my null hypothesis would be it's greater than 20. Okay, so this is the idea with a hypothesis, and we always have to break it down into two competing statements. And you'll see them abbreviate them with an H sub 0 for the null hypothesis and a H sub A for the alternative hypothesis. Sometimes other books use H sub 1 for the alternative, so 0 and 1. I don't know why they use A or 1. All right, so here's an example. A new teaching method is developed that is believed to be better than the current method. So sometimes it's easier to develop the hypothesis by considering what the research is and creating the alternative hypothesis first. So the alternative hypothesis would be what that the new teaching method is better, and the null would be that it's not any better. So that's why they call it the research hypothesis sometimes. It's like, if I've developed this new thing, so always we use the null to be like the status quo. The thing hasn't changed. So if I think something's changed, I'll say the null is it hasn't changed, and the alternative is that it has. Okay. Here, a new Salesforce bonus plan is developed to attempt to increase sales. So I'd be like, okay, my alternative hypothesis is that the new plan does increase sales, and the null would be the status quo. It hasn't changed. Okay. Or a new drug lowers blood pressure more than an existing drug. Oh, so a new drug is developed with the goal of lowering blood pressure. So the alternative would be that it actually does. The null would be that it's no different than what it's been before. Recognize with all of these tests, we're never really proving the null or the alternative hypothesis. Instead, we're coming up with a certain level of confidence that it's likely true, okay? In other words, if I give 100 people this new medicine and give 100 people a sugar pill, and then they take the new medicine for 4 months and the other people just take the placebo, the sugar pill, for 4 months, and I find that the average blood pressure of the people taking the medicine has dropped some relative to the ones who haven't, that feels like proof that the new medication works. The question is, did it drop enough that we can conclude that it was because of the medicine and not just natural variation? Because remember, there's a standard deviation, which means, you know, there could be things in people's lives that make their blood pressure go up and down and at the moment of testing. And so what we want to do is come up with some, you know, some reasonable estimate that this does appear to be having an effect or it doesn't, right? So that's what we use it for. And sometimes we use the null hypothesis as an assumption to be challenged. So like a label on a soft drink bottle states that it contains 67.6 fluid ounces. In that case, we would be like, the null hypothesis is what it states, and the label's incorrect would be the other one, right? Like we use that a lot in manufacturing, where you're like, you need to, just so you know, when you get a bag of chips and it says it's this many ounces, it's not perfectly that. They're allowed some reasonable margin of error. That would be kind of ridiculous if like you had to have it to the gram. Right, but it would also be ridiculous if there was no limit and they could just put 1 ounce in a bag that says 12 ounces and be like, well, we tried, right? So you're like, why is it mostly air? Because it's done by weight, people, all right? But even if you like look at bottles of like Coke on the shelf, you'll notice there'll be slight variations in the level, okay? They're not trying to cheat you. It's just, I mean, maybe they are, but I hope not. All right. So recognize then that when we're dealing with these hypotheses about a population mean, there's 3 types of tests we could run. Okay, 2 of them are called one-tailed tests, and then the other is called a two-tailed test. That's a little confusing until you think of the results of these tests as a normal curve. So a one-tailed test would be measuring either one side or the other. So there's a lower tail and an upper tail, and then 2 tails to the curve, okay? So a one-tailed test, always in a one-tailed test, our hypothesis is that, our null hypothesis is that the population mean is greater than or equal to the sample that we're finding. And the alternative would be that it's less than. So that's measuring the left tail. Does that kind of make sense? For an upper tail, it's measuring the right tail. And for a two-tailed test, it's when it says equal to or not equal to. Because now we've got to say, we have some measurement here, and we think the mean is not equal to that. So if it's in either area, we're going to reject it. These tails, sometimes we will call them rejection zones. Meaning, if our sample is too far away from what we think the population mean is, we would reject it and say, that doesn't seem like it's likely the cause or whatever, okay? That's a little confusing, but as we walk through it, hopefully it'll be a little less confusing. Just recognize, one thing to recognize is, am I doing a lower tailed test, an upper tailed test, or a two-tailed test? And that'll become easier as we work through it a little bit. Also recognize we're still in the same boat of, we either have a scenario where the population, we're dealing with a population mean or a population proportion that we're trying to estimate. And if we're dealing with a mean, we either know the population standard deviation, sigma, or we don't know it. Okay, so that still applies here. All right, so let's look at an example, Metro EMS. A major West Coast city hospital provides one of the most comprehensive emergency medical services in the world. Nice. Operating in multiple hospital systems with approximately 20 mobile medical units, the service goal is to respond to medical emergencies with a mean time of 12 minutes or less. 12 minutes. I'm having a heart attack. 12 minutes isn't going to cut it, right? But I guess that's what they can do. So the Director of Medical Services wants to formulate a hypothesis that could use a sample of emergency response times to determine whether or not the service goal of 12 minutes or less is being achieved. That could be hard, right? Because we can't measure every one. I would think you probably could in something like this. But I guess that would mean making your like EMS people like start a stopwatch at the time that they get the call out and then like stop it. And they probably have more important things to be worrying about than like taking the time. But anyway, so our null hypothesis would be that the emergency service is meeting the response goal. No follow-up action is necessary. And our alternative hypothesis is that they are not meeting the response goal. So they're going to have to make some adjustments to make the goal, right? Usually when you find out you're not making a goal, your options are to make adjustments so you can make the goal, or look at the goal and be like, is that goal unreasonable? Should we, not have such a stringent goal? So in this case, there's our hypotheses, okay? One more thing before we get into how to do this, there's a couple of errors that we want to try to avoid when we're doing hypothesis testing. The first is called type 1 error, and that's an error that is based on rejecting the null hypothesis when it's true. The probability of making a type 1 error is called the level of significance. Type 2 error is accepting the null hypothesis when it's false. It's super difficult to avoid this error altogether. So I don't want to go too deep into it, but those are the two types, type 1 and type 2 error you might hear a little bit more about. So here they have it just laid out in a little table for you, okay? So if we accept the null hypothesis and the null hypothesis is actually true, then we've come to the correct conclusion. But if we accept the null hypothesis that our response time really is less than or equal to 12 minutes, but it's not actually true, then we're creating a type of error, okay, type 2 error. If we reject the null hypothesis, even though it is true, that's called a type 1 error. And then if we reject the null hypothesis and it's actually false, then we've come to the correct conclusion. What we want to do is minimize the likelihood of error. And how would you guess we do things like that? Well, larger sample size, right? That's mostly it. We can increase the sample size, and we could redo or increase the confidence level of the test, which is going to, those are the two things. Problem with increasing the confidence level is it makes the thing wider, right? And so there's challenges with all of those. Here's the other thing that kind of stinks about this chapter is there's two approaches to each one of these types of tests. So like I said, we're going to have population mean when sigma is known, and then population mean, sigma unknown, and then a population proportion. But then there's two ways that we can look at it. They're the same, but anyway, one's called a p-value approach, and the other is called what do they call it? Call it a critical value approach. So let me go through what those are. So the p-value is just the probability of a computed test statistic. Okay, we know how to compute probabilities if we already have a z-score, norm.s.dist. Okay, so it's not hard, but what we have to in essence say is if the p-value is less than or equal to the level of significance, another name for the level of significance is the alpha, okay, then we're going to reject it. So it'd be like saying this: I set my level of significance or my confidence level at 95% on a one-tailed test, okay? And if my confidence is 95%, then my level of significance is the alpha, which is 1 minus the confidence level, so 0.05. So what I'm saying is, if my test statistic has a probability of less than 5%, 0.05, then I'll reject it because it's further away from the mean than I can feel comfortable saying, yes, this thing is likely true. If my test statistic has a probability of greater than 5%, I accept it, okay? That's what it means, the p-value approach. So here's what they say. Suggested guidelines on interpreting p-values less than 0.01, overwhelming evidence to conclude that something is, well, I don't like this because we're really going to compare it against a test amount, but between 0.01 and 0.05, strong evidence is true, 0.05 and 0.1, weak evidence, and greater than 0.1, insufficient evidence. So let's see. The other way of looking at this is what's called a critical value approach. So again, we're going to have a test statistic that'll be in a z-score, and then we will come up with a critical z-score, which is a z-score that if it's further away from the mean than that z-score, then we're going to reject it. Okay, so it's the same idea. I think this is getting confusing because they're giving us too much to talk about and not enough example. So I want to get to an example pretty quickly. So here's our steps. First, we develop the null and alternative hypothesis. Second, we specify a level of significance. So in a problem, it's going to be given to you, right? It's going to say, usually it will tell you there's a confidence level of this much. Just know that significance is the same as alpha, which is 1 minus the confidence, okay? Which again, something we've already done. And then we collect a sample and compute the value of the test statistic. Meaning, if we were doing a mean, we would take a sample and take the mean of that sample. That'd be the test statistic, right? With the p-value approach, then, we would use the value of the test statistic to compute a p-value, or the probability of that test statistic happening. And we would reject the null hypothesis if the p-value is less than or equal to the alpha, which was the level of significance. So, and if we were to do a critical approach, we'd use the level of significance to determine a critical value, a z-score, and then we would reject the same thing if it was less than the z-score of the null hypothesis. Okay, so this sounds confusing. It's actually not bad because it's just a carry-on of what we've been doing. So let's see. Here's an example. Hilltop Coffee. So the FTC, that's the Federal Trade Commission, wants to check Hilltop's claim that a large can of coffee contains 3 pounds of coffee. The FTC director wants to perform a hypothesis test with a 0.01 level of significance, okay? To check Hilltop's claim, suppose a random sample of 36 cans provides a sample mean of 2.92 pounds. So your first impression is like, wait a minute, we took 32 cans of their coffee and measured them, and it is less than 3 pounds. So these guys may be cheating the system by 8/100ths of a pound. Previous FTC tests show that the population standard deviation can be assumed known with a value of 0.18, and also show the population of filling weights can be assumed to have a normal distribution. All right, so think of everything we're given here. We're given a claim of 3 pounds. We're given a significance level of 0.01, which is also the same as a confidence level of 0.99, okay? We have a sample size, an N of 36, and a sample mean, X bar, of 2.92. And we have a population standard deviation of 0.18. So we could use the p-value approach, which would be to develop a hypothesis. The null hypothesis is that the claim is true, that they're greater than or equal to 3 pounds, okay? And the alternative hypothesis is that it's less than 3 pounds. Then we specify a level of significance, which was given to us in the problem and which will be given to you guys in problems. And now we're going to compute the value of the test statistic. So to do that, we're going to use this formula right here, okay, which is the mean minus the test, or minus the hypothesized amount, okay, which is 3, divided by population standard deviation divided by the square root or over the square root of n. So here's a formula we'll have to use. That's going to give us what's called a test statistic of negative 2.67. Then, if we're using the p-value approach, we'll take z of negative 2.67, and we'll find that it's the p of that by using norm.s.dist, okay, is 0.0038. And so now we're going to compare 0.0038. So what we're finding is we took this test statistic of 2.92. Right, that's what we found the mean to be on these 36 cans that we tested. And so that mean of 2.92 gives us a z-score of negative 2.67. With the p approach, then we're going to use norm.s.dist to find out that that represents the probability of it being that point or lower is 0.0038, or 38/100ths of 1%. Pretty small. Okay. So since our significance level was 0.1, which is going to be some point over here, we're going to reject the null hypothesis. In other words, what we're saying is, given all of this data, okay, given a mean of 2.92 and a population standard deviation of 0.18, do we think that this mean of 2.92 truly and really represents the fact that it's less than 3 pounds, or is it just within natural variation? And we're saying is the probability of having a mean of 2.92 out of a sample of 36 is 0.0038, which means which means we're going to reject that null hypothesis and say they really are less than 3 pounds, because the null hypothesis was that it was 3 pounds or greater. So in other words, we're saying this is enough below the mean that it's not just due to happenstance or to random error, that truly their cans are underweight. Okay. So it's a little confusing. Okay. If we use the Z approach or now they're going to show us the pictures. Sorry, which is what I was trying to draw up there. So we're saying the p-value of this area is 0.0038, but our significance level is 0.01. And so this is more extreme of a result from this sample than we would expect to see if it was just due to random chance. To use the critical value approach, instead of we would determine a critical value by taking the alpha of 0.01, finding a z-score of that, negative 2.33, then we find our our test statistic, and we find that our test statistic is further away from the mean than our critical value. So it's the same idea. One uses probability and says, if the thing you find from your sample is further away or less, has a lower probability than your alpha, then you're going to reject it. If it has a higher probability than your alpha, you're going to accept it. Okay. Whereas this one says if it has a lower z-score or a z-score that's further away from the mean, then you'll reject it. And if it's closer to the mean. So it's the same idea. One just uses a z-score, one uses probability. I always feel like the p-value is sort of silly because it takes an extra step of converting that z-score into a probability. Why not just use the z-score? All right. So that's when we know the population mean. Again, so there's our z of. So again, what we're saying is, here's the mean. Here's the critical score. So here's the critical score. So if the sample we take is a more extreme, further away from the mean, then we reject it and say, no, that can't be due to random chance. That's got to be due to some actual difference. With a two-tailed hypothesis test, now we're checking if something is equal to or not equal to, meaning we're splitting the rejection range. It could be we could reject the hypothesis on either end. Okay, if something is too far greater or too far less than the mean, we would reject it. So the critical values will be that we use instead of just the z-score will be the z of alpha divided by 2, because we're saying, so if our alpha is 0.05, then we're going to say the rejection range is 0.25 on the top and 0.25 on the bottom. Okay, so it's a little bit. So here's Max Flight Inc. Let's look at the example. Max Flight produces golf balls with a mean driving distance of 295 yards. Its quality control program involved taking periodic samples of 50 golf balls to monitor the manufacturing process. Quality assurance procedures call for the continuation of the process if the sample results are consistent with the assumption that the mean driving range distance is 295 yards. I'm assuming they have something that strikes the balls with the same amount of force each time. I don't know how they do it. What's that? Yeah, golfing robot. Otherwise, the process will be adjusted. So again, they want to say, okay, is this thing, and I would guess in their situation, they don't want it to go further or shorter than that. They want it to be a consistent ball, right? We strike it with the same amount of force in the exact same place, it's going to travel a certain distance. So assume a sample of 50 golf balls. He perked up. He was like, golf. Yeah. A sample of 50 golf balls provides a sample mean of 297.6 yards. The population standard deviation is believed to be 12 yards. Perform a hypothesis test at the 0.05 level of significance to help determine whether the ball manufacture process should continue or should be adjusted. Okay. So really what we're saying is, if we think it's 295, but we just took a sample of 50 and got 297.6, does that tell us that, is that just within the parameters of normal variation, or is it outside of those parameters and we need to fix our process, is really what we're asking. So the first thing we're going to do is create our hypothesis. So whenever it's two-tailed like this, meaning we're willing to reject it if it's too high or too low, then it'll be presented like this. The null hypothesis is that the mean, the population mean equals 295. And the alternative is that it does not equal 295. It is either less or more than that. Then we're going to specify our level of significance, which was given to us as 5% or 0.05. And then we're going to compute the test statistic, which again is the mean of the sample minus the hypothesized amount, or the goal, in this case 295, over the population standard deviation divided by the square root of n, and that gives us a test statistic of 1.53. In other words, our mean from our sample came out to be 1.53 standard deviations above what we hypothesized it would. Okay. So to do the p-value approach, we would just compute the probability of that z statistic. The probability that z is greater than 1.53 is 0.9370. So the probability that it's less will be 1.260. And you notice they multiplied it by 2 because it's a two-tailed test. Okay. And it'll make more sense when we see the picture. Determine whether to reject the null hypothesis, because a p-value of 0.1260 is greater than the alpha of 0.05, we will not reject the null hypothesis. So here's what we came up with. So this became our critical areas, okay, 1.53 plus or minus it. And our test statistic came out to, what was it? 0.1260. Is that right? So what we're saying is, it is yeah, so the probability ones always confuse me a little. Sorry, guys. So it is, they're not giving us, so here's my probability, 0.630 for 1.53, and our p-value is 0.126. That's confusing to me. I'm going to move on to the Z one, and maybe I'll be able to explain it better from there and then come back to it, because I've never used p-values because I feel like they're confusing. Whereas the Z makes more sense to my brain. But so here's our critical value approach. Okay. So we would first determine our critical value, which is the alpha divided by 2, and then find the Z score for that. So if alpha 0.5, we divide it by 2 to get 0.025 and take the Z score of 0.025, it'll be plus or minus 1.96. So what we're saying is if the test statistic comes out to be less than a Z of 1.96, negative 1.96, or greater than a Z of positive 1.96, we're going to reject that. That means it's too far away from the mean to conclude that it was just due to random chance. Okay. So our test statistic that we calculated already was 1.53. So it's going to fall. So it confuses me that we have this. So it's going to fall like right here. Okay. Which means we're not going to, we have to assume that this process is in control, meaning that those little variations were close enough to the mean, what we'd expect given that standard deviation and the sample size, that we can't conclude that it's something off, right? And so if we go back to the probability one, I guess what's confusing me is the way they have this laid out on here, is we're saying, so we come up with the test statistic. From there, we compute the probability, and we say the probability of getting a Z of 1.53 on a two-tailed test is going to be 1.260 on either side. And since that probability is greater than what our alpha is, a 0.5, so it's more likely that this thing is within control than it's out of control, we're going to reject the null hypothesis. I mean, not reject the null hypothesis. Sorry, guys. I'm afraid if I'm confusing you worse, but it'll work when we go do a guided, right? Yeah, I'm not a big fan of the p-value one. All right. Here's the Excel functions that we will use, although I often don't use count for sample size unless it's a really huge sample. I just like look at it and be like, yeah, it's 50. Sample mean is average. We know that. So to find that standard error, that's where we just take the population standard deviation divided by the square root of the sample size, and then to find our test statistic, we're just going to take mean, the sample mean, minus D8, which is a hypothesized value, divided by the standard error. Okay, and that was the formula I was telling you you're going to need. Okay, not bad once you figure it out. The p-value of the lower tail is norm.s.dist of the z-score of the test statistic and true. Of the upper tail is 1 minus the lower tail. And of the two-tailed test, you just multiply it. What they put? Min, D13, D14. I've never used that MIN function. Maybe we'll have to play with that. Like I would just multiply it by 2 and the standard deviation by 2. I mean, not standard deviation, the absolute value of it by 2. All right. Recognize now, since we've already been doing interval estimation, that a confidence interval contains a hypothesized value. A confidence interval that contains the hypothesized value we do not reject. Otherwise, we do reject it. So the simple random sample from a population, I'm just going to read this to you so I don't confuse things more. Select a simple random sample from a population and use a value of the sample mean to develop a confidence interval for the population mean. This is what we've already done. And so I guess what they're trying to get at here is we've already done this concept of creating this range, right? The interval. But when we do that interval here, we're just considering the part outside of the interval to be a rejection range and inside the interval to be the accept. So it's the same concept, but it gets confusing because we're looking at it from, I guess, a different perspective. Okay. And then the p-value thing is really looking at a different perspective because we've done everything with z-scores. Well, I mean, we've done probabilities too, but so if we consider like the max flight example we just used, we could look at a 97% confidence interval. We would see that interval, using what we did last chapter, would be between 294.3 and 300.9. And so since our mean is assumed to be 295, it falls within that interval, so we don't reject it. Okay, so it's the same idea of what we'd already been doing. There's a whole nother bunch of slides that I'm not going to go through on what if we don't know the population mean. I mean, the population standard deviation, sigma. And the reason I'm not going to go through them is it's the exact same process, except we use the t-distribution instead of the normal distribution. And we use the S, the sample standard deviation, instead of the population standard deviation. And so if we don't know the sigma, we use t and use sample standard deviation. If we do know the sigma, we use norm and we use the population standard deviation, just that. So that's the exact same as last chapter, right? Those two things, if you think about it, were identical, except one used the t-distribution and the other used the normal distribution. So I just didn't think it was worth like spending hours on. And the rejection rules are all the same, except instead of z, it's t. Okay. So the Excel functions we would use, same thing, except for when we get down to the p-values, instead of norm.dist, it's t.dist. That's all. All right. So again, just a reminder, when we're doing a one-tailed test, our null hypothesis is that the probability is going to be greater than or equal to that's confusing. That should be HA here. So there's an error on the slide. So our one-tailed, our null is that it's greater than or equal to when it's a lower tail, and our alternative is that it is less than. On a one-tailed upper, the null hypothesis will be to be less than or equal to, and the alternative would be that it is greater than. And then on a one-tailed, it's going to be equals and not equals to. I mean, sorry, a two-tailed, equals to and not equals to. All right, here's the formulas, like I said, that you'll need to know for, well, I mentioned you needed it for the mean one, so this is for the population proportion. So to calculate the test statistic, you're just going to take the sample proportion minus the assumed proportion or hypothesized proportion divided by the standard error of the proportion, where the standard error of proportion is the assumed proportion times 1 minus the assumed proportion over n, the square root of all that. So again, this isn't new. Again, the same idea. There's a p-value approach. So if the p-value is less than or equal to the alpha, that'll be our null hypothesis. And we'll, again, so once we get a p-value, a probability, or a z-value, a critical value, the rules are all the same, right? If our test is that the probability is finds that the probability is greater than the null, then we're going to reject it. So same idea. All right, so that's another golf course, Pine Creek Golf Course. Over the past year, 20% of the players at Pine Creek were women. In an effort to increase the proportion of women players, Pine Creek implemented a special promotion designed to attract women golfers. It was probably sexist. Okay. Right. Anytime people are like, we're going to assume women like this, so we're going to do a promotion that has this thing that women are going to like, that's kind of sexist, right? Like, unless they involved women in the decision making of what would be that promotion. I think it's sexist that women get to drive from closer T's personally. Not fair, man. Equality. Everybody drives from the same T. Does that make sense to you? At least one person agrees with me. The manager now wants to determine if the proportion of women players has increased. A random sample of 400 players was selected, and 100 of the players were women. So that's 25%, right? 100 over 400. And the level of significance is an alpha of 0.05. So same idea, we're going to determine the hypothesis. So the null is that it is greater than or equal to 20%. I'm sorry, less than or equal to 20%, what it already was. And the alternative is that it is greater than 20%. It's gone up, okay? We specify our level of significance, 0.05. So we're going to compute our test statistic, which is just the square root of 0.2 times 1 minus 0.2 over the n. And we take the square root and we get 0.02. And then we're going to find our test statistic, which is our sample, 0.25, minus our assumed test statistic, 0.20, over the standard of the proportion, gives us 2.5. All right. So again, we can do the p-value approach and say for a z of 2.5, the lower tail would be 0.9938. 1 minus that is 0.0062. So the probability of us getting this test statistic is 0.0062. And since that is less than our alpha, we're going to reject the null hypothesis and say, we really do believe that it has changed. Okay, yeah. Okay. So again, with the p-value approach, if our p-value is less than alpha, we're going to reject the null hypothesis. I think maybe that's an important, just remember that piece, right? Instead of getting all confused like I did a minute ago, just remember if the p-value, the probability of our test statistic being what it is, given all of the data we have, is less than our alpha, then we're rejecting the null. We're saying there really was a change. Because to accept the null means we don't have evidence to say there was a change, right? Like it may be different from what we assumed, but it's not enough different that we can conclude that it's not just due to chance or whatever. So to use Excel to determine p-values, this is stuff we've already used, okay? Standard error, we have to create our own little function, the square root of the hypothesized value times 1 minus hypothesized value divided by the sample size, the test statistic, which is going to be what was that one? The n minus the hypothesized value over standard error. Okay, so it's just our sample, our proportion minus our hypothesized value proportion over the standard error. And then norm.s.dist. So it's, if we're going to use the critical value approach, instead of converting it to a probability, we're just going to use the z value. So we're going to say, okay, the z of 0.05 is 1.645. So because 2.5 is greater than 1.645, we reject the null hypothesis and say there really has been a change. There's more female golfers now. So our promotion must have worked, okay? All right, I apologize to you guys if I got my getting a little mixed around in there, caused you to get more mixed around. I really do think that this chapter is not too bad once we get a handle on what we're doing. It's still the same thing. Are we dealing with a mean that we're trying to, as our parameter, we're trying to estimate whether or not it's correct, or are we dealing with a proportion? And then if we are dealing with a mean, do we know the population standard deviation or do we not? And those are the main things that kind of direct how we attack the problem. and then there's added to this, do they want us to use the p-value approach where we find the probability and compare it to the alpha, or do they want us to use the critical value approach where we just compare the z-scores of our null hypothesis and our test statistic? And that's really it. So I mean, as hard as that sounds, it's my bad for, I think, making it sound harder than it really was. So I hope you guys have a terrific day, and we will be looking at a guided assignment on this on Friday. Not Friday, on Monday, because I'm gonna be fishing on Friday. I hope you guys get to go fishing too, or whatever you like to do.